We are continuing our study of integer division by looking at the greatest common divisor of two integers and something called Bezout's lemma, which is closely related and has to do with the greatest common divisor. Here's the usual outline. We will first talk about greatest common divisors and then Bezout's lemma. So here's our official definition, or at least the first form, assuming that at least one of the integers a and b is not 0. This has to be the case in order for a and b to have a greatest common divisor. Then the greatest common divisor of a and b is the largest integer d, for which d is a divisor of a and d is a divisor of b. So this definition doesn't really say anything more than the phrase greatest common divisor. Some notation for the greatest common divisor. The usual notation. The greatest common divisor of a and b is denoted by GCD of a comma b. Now here's a second version of the definition in a little more detail. So we have two integers again, a and b, at least one of which is non-zero. The greatest common divisor is the integer d, for which d is a divisor of a and d is a divisor of b. These two formulas say that d is a common divisor. And the second requirement, for every integer n, if n's a divisor of a and n is a divisor of b, then n is less than or equal to d. This is the part that says d is the greatest of the common divisors. One thing we can notice right away, for every two integers a and b, 1 is a common divisor of a and b. So that means that the greatest common divisor of a and b will always be greater than or equal to 1. And this will help us out a little bit. This means that when we are looking for greatest common divisors, we can restrict our attention to positive divisors. So let's try the finding the greatest common divisor of 30 and 25 using the definition. So the plan is to list the divisors of 30, and we will list only positive divisors. The positive divisors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. Then we'll list the positive divisors of 25, just 1, 5, and 25. The common divisors, the numbers that appear in both lists, are 1 and 5. And the greatest of the common divisors, the largest in this third list, is 5. So the greatest common divisor of 30 and 25 is 5. The method from the previous slide is not very efficient if you're dealing with large numbers. So we're going to describe a much more efficient method, which uses the division algorithm from our last set of slides. So there are two things we have to know in order to understand this procedure for finding the greatest common divisor. First of all, what I've called fact 1. For any two integers a and b, at least one of which is not 0, the greatest common divisor of a and b is the same as the greatest common divisor of the absolute value of a and the absolute value of b. This means that when we are calculating greatest common divisors, we can ignore signs, pluses or minuses. So for example, the greatest common divisor of minus 30 and minus 25 is the same as the greatest common divisor of 30 and 25, which is 5. The second fact that we'll have to know to understand why this algorithm that we're going to discuss for finding greatest common divisors works is this. Assume A and B are both positive integers. If you use the division algorithm to divide A by B, you remember you get a quotient and a remainder. So I've called the quotient Q1 and the remainder R1 in this equation. Dividing A by B gives you an equation, A equals Q1B plus R1. And as we know, the remainder will always be non-negative and less than the thing you're dividing by, which is B in this case. Okay, under these circumstances, if A is written as Q1 times B plus R1, then the greatest common divisor of the two original numbers, A and B, is the same as the greatest common divisor of B and the remainder. We'll look at a proof of that fact later. Right now, let's just try an example of fact number 2. So if we divide 30 by 12, so in this example, the A is 30 and the B is 12, we get a quotient of 2 and a remainder of 6. 30 is 2 times 12 plus 6. And now, according to fact 2, the greatest common divisor of 30 and 12 is the same as the greatest common divisor of 12 and 6, which is pretty easy to verify. The greatest common divisor of 30 and 12 is 6, and the greatest common divisor of 12 and 6 is 6. So now let's talk about the procedure for finding the greatest common divisor of two integers, at least one of which is not 0. And we will assume in this procedure that both integers are positive. So assume A is greater than B and both A and B are positive. To find the greatest common divisor, we are going to use the division algorithm repeatedly. We will first divide A by B. That will give us A equals a quotient times B plus a remainder. And then, using the fact that the greatest common divisor of A and B is the same as the greatest common divisor of B and R1, B and the remainder, we will repeat the procedure. We will divide B by R1. And that process will continue, and I think looking at an example is probably the best way to see how this works. So we are going to find the greatest common divisor of 52,835 and 305. So we divide the larger of the two numbers by the smaller, and we get a quotient of 173 and a remainder of 70. So according to fact number 2, the greatest common divisor of the two original numbers, 52,835 and 305, is the same as the greatest common divisor of 305 and the remainder, which is 70. So we have reduced the problem to finding the greatest common divisor of two much smaller integers. So we are going to repeat the procedure. We will divide 305 by 70. If you divide 305 by 70, you get a quotient of 4 and a remainder of 25. So using fact 2 again, that tells us that the greatest common divisor of 305 and 70 is the same as the greatest common divisor of 70 and the remainder from the second division, namely 25. We have reduced the problem again to finding the greatest common divisor of two even smaller numbers. We repeat the procedure. We're going to divide 70 by 25. This can be done pretty easily without a calculator. The quotient, when you divide 70 by 25, is 2, and the remainder is 20. So fact 2 again tells us that the greatest common divisor of 70 and 25 is the same as the greatest common divisor of 25 and 20. Now, at some point in this procedure, you may recognize what the greatest common divisor is. But I'm going to carry the procedure all the way to its end. So now I'm going to repeat the procedure with 25 and 20. Again, an easy division. 25 is 1 times 20, a quotient of 1, that is, and a remainder of 5. So the greatest common divisor of 25 and 20 is the same as the greatest common divisor of 20 and 5. And now, one more time, we will divide 20 by 5. 20 is 4 times 5, the quotient is 4, the remainder is 0. So when you get a remainder of 0, as we did here, we know that 5 is the greatest common divisor. 5 is a divisor of 5, and according to this equation, 5 is also a divisor of 20, so it's the greatest common divisor. So when you get a remainder of 0, using this procedure, you know that the remainder from the previous step is the greatest common divisor. In this case, the greatest common divisor is 5. So, our conclusion, the greatest common divisor of 52,835 and 305 is 5. Here are some easy properties of greatest common divisors, which we will be using and which you can feel free to use. They follow from the things we know about the divides relation. The greatest common divisor of A and B is the same as the greatest common divisor of B and A. This series of equations simply says that when you're calculating greatest common divisors, pluses or minuses don't matter. If you're calculating the greatest common divisor of two numbers and both are negative, it's good enough to calculate the greatest common divisor of their absolute values. As long as A is non-zero, the greatest common divisor of 0 in A is A. So you remember, every integer is a divisor of 0. So the greatest number that divides A is A. Therefore, the greatest common divisor of 0 and A will be A. The greatest common divisor of 1 and A is 1. 1 only has a single positive divisor, namely itself. Fact number 5, if P is a prime number, here's the definition of prime number. This is something you probably know at this point. P, a prime number, means P is greater than 1, and the only positive divisors of P are 1 and P. So greater than 1 and only two positive divisors, 1 and itself. So we have a prime number, and we also have another integer A, which is not divisible by P. So if P is prime and P does not divide A, then we can say what the greatest common divisor of A and P is. Right? The divisors of P are 1 and P, so the greatest common divisor has to be one of those. But p does not divide a, so that narrows it down to the number 1 for the greatest common divisor. If p is prime and p does not divide a, then the greatest common divisor of a and p is 1. And now we come to the second part of these slides, what is known as Bezout's lemma, or sometimes the linear combination theorem. I will always refer to it as Bezout's lemma. Take any two integers a and b, at least one of which is not equal to 0. This is what we need to know that a and b have a common divisor. Okay, so under those circumstances, there are integers s and t such that the greatest common divisor of a and b is s times a plus t times b. In other words, you can write the greatest common divisor of a and b as a linear combination of a and b, where the coefficients, s and t, are integers. So we will explore the proof of Bezout's lemma in the exercises. Well, let's look at an example without any calculations. The greatest common divisor of 12 and 7 is 1. And according to Bezout's lemma, that means that 1 can be written as some linear combination of 12 and 7. And here's one way of doing it. Minus 4 times 12 plus 7 times 7. So the s in this example is the multiplier for 12, which is minus 4. The t in this example is the multiplier for 7, which happens to also be 7. And now, how do you find s and t? As it turns out, the calculations that we did in the division algorithm, finding the greatest common divisor can be used to find s and t. So this is a fairly quick procedure even for very large numbers. And we are going to see how it works by looking at this example. So in example 2, we found that the greatest common divisor of 52,835 and 305 is 5. And here I've written down the steps that we went through to find that greatest common divisor. We first divided 52,835 by 305, got a quotient of 173 and a remainder of 70. And then we divided 305 by 70, then we divided 70 by 25, then we divided 25 by 20, and then we divided 20 by 5, and that was the step where the remainder was 0. So what I've written down here are the steps in finding the greatest common divisor, except for the last one, where the remainder was 0. We won't need that step in this calculation. Okay, here's a quick description of what we're going to do. Oops, not quite. First, we're going to replace 52,835 by A and 305 by B. One reason for doing this is there's less writing. And the real reason is that this just makes it easier to keep track of things. So you don't have to do this, but I strongly suggest that you do when you're using this procedure. Okay, so here we go. The first equation with 52,835 replaced by A and 305 replaced by B would look like this. And the second equation, let's see, 305 occurs in that equation, so we're replacing the 305 by b. So we now have the replacements a and b in the first two equations. And now here is a short description of what we're going to do. Starting with equation 1, right here, we're going to solve each equation for its remainder in terms of a and b. So let's start. We're solving equation 1 for its remainder, which is 70. And actually, we're looking at this form of equation 1 with the a and the b. Solving for 70 in terms of a and b is fairly simple. We just subtract 173 times b from both sides. So 70 is a minus 173b. On to the second equation. We want to solve the second equation for its remainder, which is 25. So we're to isolate the 25, we're subtracting 4 times 70 from both sides. 25 is b minus 4 times 70. And now from the result of the first equation, we have 70 in terms of a and b. So we're going to replace the 70 in this red equation by a minus 173b. Which I did here. I simply replaced 70 by a minus 173b, and then I distributed the minus 4 in combined like terms. Minus 4a plus 693b was the result. Okay, on to the third equation. Here the remainder is 20. So we're solving for the remainder. Subtract 2 times 25 from both sides. And now from the result of equation 1, we have 70 in terms of a and b. And from the result of equation 2, we have 25 in terms of a and b. 25 is minus 4a plus 693b. So we're going to make those two replacements, replacing 70 by a minus 173b, and replacing 25 by minus 4a plus 693b. And now, again, I distributed the minus 2 in combined like terms. I'm not putting all the algebra down here. Fairly straightforward, and I got 9a minus 1,559b. And now, on to the fourth equation. Want to write the remainder in terms of a and b. And here, the remainder is the greatest common divisor. So once we've finished writing the remainder from equation 4 in terms of a and b, we will be done. So subtract 20 from both sides. Using the result of equation 2, 25 is b minus, 25 is minus 4a plus 693b. That's going in here for the 25. And from equation 3, 20 is equal to 9a minus 1,559b, so that's going in here for 20. There's the substitution. If you distribute the minus sign, combine like terms, you get minus 13a plus 2,252b. We're done. We have written the greatest common divisor as some integer times a, the first of the two numbers, plus another integer times b. B was 305, the second of the two numbers. So the s is minus 13. That's the multiplier for a. And the t is 2252.